Okay, so thanks, Professor Esposito. Okay, Professor is a kind of spoiler here. He gave you some hint about my work. So today I'm going to introduce you a model, a complete formulation for the minimum creep rate, considering both the dislocation and diffusional contribution. And at the end, we will validate this model with some experimental data related to the 316H stainless steel. Okay. Briefly, this will be my agenda. So just introduce the scope and the objective of the work. Then I will introduce the complete formulation. And then with the experimental data of the 316H steel, we will try to carry out some results and conclusion. So, although the diffusional creep flow is often not considered as really interesting for engineering applications, let's say the need of a model capable to take into account both the dislocation and diffusional contribution is justified by the increasing demand of reliable creep result. And the extrapolation based on creep models formulated and validated mainly for dislocation type creep may underestimate the actual creep rate, providing, let's say, not inaccurate results in case of diffusion mechanisms. Recently, Bonora and Esposito already proposed, let's say, a first stage of mechanism-based formulation. Here we are going to add also the diffusional contribution to this formulation. And at the end, as I said, we will validate this mechanism with some experimental data found on the region. Depending on stress and temperature, there are mainly two different deformation mechanisms. So we are talking about dislocation, so dislocation glide or dislocation glide plus climb, or diffusional creep. For each of these mechanisms, there are specific models available in the literature, which are most of them in a form of an n-power law solution, like this one, where the term A can be explicited for the temperature in terms of Arrhenius law. In case of diffusional flow, there is a linear dependence of the creep rate with the strain, while talking about dislocation creep, this value of the n, the strain rate is going to be proportional to the power of the stress. That means that if we have a constant value of n and a, which can be, I don't know, 5, 10, in case of low stress value, the creep rate can be largely underestimated. So it seems that experimental creep data relative to a wider stress range seems to indicate the existence of an exponential dependence of the creep rate on the stress. And this behavior can be explained as a result of the gradual change in the creep mechanism, going from dislocational to diffusional, so from high stresses to low stresses level. And this cannot be described by conventional models with the constant value of the creep exponent n. So, through an explicit dependence of the exponent n on stress, here we are going to propose a model which takes into account the different change of mechanisms from dislocational to diffusion. So, the minimum creep rate can be seen as a sum of two contributions. The first one is the dislocational contribution, and the second one is the diffusional one. Then, considering the Barton equation related to the diffusion theory, we have that the minimum creep rate for the diffusional contribution is proportional to the product between the vacancy diffusion flux and vacancy concentration, plus the ratio between the atomic volume and the average grain size. If we explicit the dependence of the vacancy diffusion flux in terms of vacancy diffusion coefficient and atom diffusion coefficient, we have this equation in the line quotes. If now we consider the contribution of the dislocational mechanisms, where we can see there is an explicit dependence of the stress level for the exponent and as I was talking before, while for the diffusion part, the exponent is equal to 1. And it's also convenient to consider a threshold value of the stress below which the process, the mechanism of the dislocation and diffusion is kind of, let's say, inhibited. Here we consider just the one related to the dislocational contribution because the one related to the diffusional one is very low. So putting the equation in a more, let's say, friendly way and expliciting the dependence on the temperature and on the activation energies for both dislocational contribution and diffusional contribution, there are 3 situations which can be highlighted. Okay, so the first one, okay, we have the plot of the double block state of nominal stress and minimum creep rate. In red, there is the total creep rate. We see that at low stresses, it can be that the dislocation contribution is greater than the diffusion one, and we see there is a smooth transition going from low to high stresses. This condition is typical for poor metals having large grain size and limited sources of vacancy. Second situation is when the diffusional contribution is greater or equal or greater than the dislocational contribution. And we can see that going from quite low stress level to quite high stress level, there is a kind of sharp change in the slope of the total creep rate. This is a typical behavior for poor metals having fine grain size and hardened alloys with extensive sources of vacancies. Then there is a third situation. Let's say we just can theorize that. We don't have an evidence in experimental data yet. Here we can see that the role of the threshold value is we have this threshold value on the, let's say, changing from the diffusional contribution to the dislocational contribution. So in order to validate this model, we found some data in the literature related to the 316H stainless steel. The data are mainly from Gorman and Zhu, Bloch, Fiala, Whittaker, and by the Japanese National Institute for Material Science. And as we have a wide range of minimum creep rate, and we are sure that there are different deformation mechanisms which are activated by different activation energies. In this study, we are not considering a different grain size for the data. So we have normalized the minimum creep rate through the temperature with the activation energy. And okay, let's say the activation energies are kind of consistent with what we were expecting. And here we have, with the black curve, the dislocational contribution of our model and all the data we were collecting. As you can see, the data which are related to the deformation of the dislocation mechanisms are gathering all together a line on this black line. We obtain this because with the normalization we are, let's say, allowed to aggregate all the data which, let's say, show us the same deformation mechanisms. While for these data which are scattered from from this curve, it seems that they are not related to this kind of deformation of mechanism. Indeed, choosing an adequate activation energy for the diffusional contribution, we see that those data that were scattered on the other plot here are all together on the line related to the diffusive model. So in this plot, we have all the model, so the proposed model consisting of both dislocational and diffusional contribution. We can see that the trend is consistent with the experimental data. For the ones here on the top, here we can see we are supposing that the threshold value will, let's say, have an important role for the description of the minimum frequency. So, concluding, the proposed model follows the mechanism's evolution according to the deformation mechanism maps. Then the model is able to predict the nonlinearity of the double log plots, minimum creep rate and stress, both for high stresses with the threshold stress value and also at low stresses. Then the activation energy used in the model to obtain the correct values of the minimum creep rate are consistent with the experimental measured values. And then we demonstrated the applicability of the model with the 316H stainless steel data. I finished. Thank you.